Hey there, welcome to another part on Module 2. In this one, we'll be discussing further topics on the basic computer organization. The topics that we'll be covering in this is computer instruction, the instruction code format, basic computer instructions, the completeness of an instruction set, and timing control. The computer instruction. So the computer instruction has three code formats. Each format has 16 bits. The opcode consists of 3 bits and the remaining 13 bits depend on the type of opcode. So whatever operation will be performed, on the basis of that we can determine the remaining 13 bits. The three types of instructions are memory reference instruction, register reference instruction, and input output instruction. So the memory reference instruction is as follows. Since the instruction code format is of 16 bits, the first 12 bits are for the address, 3 bits for the opcode, and the last 15th bit for the addressing mode. The condition for memory reference instruction is that the opcode has to be between the range of 000 till 110. So any value of opcode between these two values, including these values, means that it is a memory reference instruction. It can have either of the two modes, whether it is direct addressing or indirect addressing. So it could be 0 or 1 at the 15th bit, and the opcode will be between these ranges. The register reference instruction, on the other hand, has a fixed opcode and the addressing mode. So from bit number 12 to 15, the code has to be 0, 1, 1, 1. Whenever the opcode is 1, 1, 1 and the addressing mode is 0, that means this is a register reference instruction. The address is used for determining the register operation. At the third type, we have the input output instruction. For this, the opcode and the addressing bit, all of them are set to 1. So we have 1, 1, 1, 1 for the 12th to the 15th bit, and this sort of sequence determines that it is an input output instruction. The bits from 12 to 15 are the ones that determine the type of instruction. If the opcode or bits 12 to 14 are not 111, then it means it is a memory reference instruction. That means any combination of the opcode below 111 is a memory reference. The remaining ones are register reference or input reference. The difference between the register and input is the addressing mode, which is 0 in register and 1 in input. So as you can see, the opcode in the previously discussed example has only 3 bits. That means the 3 binary combinations, 3-bit binary can make 8 different combinations. Thus it shows that this sort of computer has a maximum number of 8 different operations. However, since register reference and input output instructions use the remaining 12 bits, okay, so the 12 bits can also be used as a part of operation code. Thus the total number of instructions can exceed 8 different types. Here we'll be discussing some basic computer instructions. The symbol for the instruction will be given here. We will have the hexadecimal code for the instruction and what the instruction performs. The first part of the table refers to memory instructions. These instructions are done by the memory and are special to memory reference instructions. This part of the table refers to instructions for register referencing, and this is for the input output reference registers. We'll be discussing them in detail one by one. The memory references instruction has an address part of 12 bits. The address part is denoted by 3 x's and stand for the 3 hexadecimal digits corresponding to the 12-bit address. So we have a 12-bit address which is represented by 3 x's, and each x stands for a hexadecimal digit, and that's how the 12-bit address is made up. The last bit is designated by the symbol I. When I is 0, the instructions have the last 4 bits of the hexadecimal equal from 0 all the way to 6, and when the I bit is 1, then the hexadecimal last 4 digits range from 8 all the way to E. As we can see here in the table, When I is set to 0, we have it from 0, 1, 2, 3, 4, 5 and 6. At 1 it starts from 8 and goes all the way towards E. We need to learn the symbols, the description, okay, the operation that is being performed at each of them, because the questions that are asked on this sort of topic are that they will be giving you a binary number which you have to convert into hexadecimal number, and then you will have to define out what the operation is. Hence you need to learn the operations, and you also need to know that at I referencing 0 the ranges are from 0 to 6. For 1 it's from 8 to E. The register reference instruction uses 16 bits to specify an operation. So the leftmost 4 bits are always 0, 1, 1, 1, and this number is equal to 7 in hexadecimal. The other 3 hexadecimal digits give the binary equivalent of the remaining 12 bits. So whenever we have the following table, this will be for the register reference. The 4 bits, the hexadecimal 4 bits in the end, the last 4 bits are going to be a 7 always, and the remaining 12 bits, and why are we saying 12? Because 3 hexadecimal, that means 4 bits each, so 4, 8, 12. So we'll be having 12 bits over here, that will be referring to the binary numbers. As for the input output instruction, they also use all 16 bits to specify an operation. The last 4 bits in this case are always 1, 1, 1, 1. We studied all these cases in the requirements for the memory to be identified, and hence the equivalent hexadecimal is F. As we see in the table, the leftmost 4 digits will be F, and the other remaining 12 bits are going to represent the numbers. We also have to discuss the instruction set completeness. So what this means is the set of instructions are said to be complete if the computer includes enough instructions in each of the following categories: arithmetic, logical and shift instructions, instructions for moving information to and from memory as well as the processor's registers, program control instructions together with instructions to check status conditions. Most computer systems are supposed to have all of these instructions within them, which is only when it's said to be a complete set of instructions. If these instructions are missing, then it is impossible for the computer system to perform basic operations such as adding or moving data or transferring data from memory to the processors and so on, which will cause incomplete set of instructions, hence leading to the inability to perform certain tasks. We also need to have input and output instructions that will allow you to input data and the outputting of data after the execution of instructions. Timing signals and control. So the timing signals are generated by a master clock that controls all the timing for registers in the basic computer. Flip-flops and registers in the system are synchronized with the clock pulses, and these clock pulses do not change the state of the register. So the register does not change unless the register is enabled by a load. As we discussed earlier in the bus system, that LD has to be set to 1 in order to load data onto the register. So the clock pulse does not cause change in a register unless the register is open to change. The control signals, on the other hand, they are generated by the control unit, and they provide control inputs for different components such as multiplexers in the common bus, and control inputs for the processor registers, and micro operations for the accumulator, for the ALU. Each and every one of these components that require control inputs, the control unit provides them, and these control signals are the selections that are given to them. There are two types of organizations for these controls. One is hardwired and the other one is microprogrammed. The hardware control is basically applied using logic. So we use gates and flip-flops, decoders and other digital circuits. We use components and we implement the logical circuits for the control system. The microprogrammer, on the other hand, is the control information is stored in the control memory. So this is more like the program itself. So these instructions are stored as a program, as a set of instructions, instead of being hardwired and logically made. And these can easily be changed and updated. If while While on the other hand, in the hardware control, if you need to change it, you have to change the entire circuit that you have made. That is the advantage of microprogram control. In the hardware organization, the control is implemented with the gates and flip-flops, decoders, other digital circuits. Microprogram control is when the information is stored in a control memory. So if the design is modified, the control memory has to be updated, and there is no need to change the circuitry and all. This is the basic hardware control organization for a basic computer system. We have the instruction register. Okay, so the instruction is bought and saved into the instruction register from the memory, and then we have a whole system of control logic gates that have been implemented in order to perform certain operations. We have a 4-bit sequence counter. Okay, and it has the features of a increment, clearing, and a clock. We have two decoders in this. The first decoder over here is used for transferring the opcode. Okay, since we have 3 bits for the opcode, there are 8 possible different combinations. Hence we have a 3:8 decoder used that will give us the outputs from D0 to D7. So D0 refers to the opcode being 000 all the way to D7, referring it to be 111, and this will also help us identify the memory reference or register reference or the input output on the basis of the opcode that is being transferred, and accordingly we will be having control signals that will be generated. The 15th bit, that is the addressing mode I, it's stored in the flip-flop I, and it is also given to the logic gates in order to perform certain operations. We get the address of the operand from the instruction register, and it is also sent to the logic, and then the timing signals are sent through a decoder from the sequence counter ranging from T0 all the way to T15, and they too are set to the sent to the control logics for the timing and to determine at what timing signal which certain controls have to be sent. This here is a timing diagram, so generated by a 4-bit sequence counter and 4x16 decoder. The sequence counter can be incremented or cleared. Example is T0, T1, T2, T3, T4, T0, T1. So the cycle is going to stop at T4 and it's going to start at T0 again. This is because at the time T4, sequence counter is cleared to 0 if the decoder output D3 is active. So this is our condition, because of which sequence counter is cleared to 0. Thus our timing signal starts from T0 after T4. This happens because when we initially start our clock, the timing T0 is set to active in our first clock pulse. The distance between the clock from here to T0 is the first clock pulse. This will be the second pulse. So in the first pulse, T0 is active, and once that pulse is completed, we have T1 active in the second clock cycle, and we have T2 active in the third clock cycle, T3 active in the fourth, and T4 active in the fifth. As we see, at T3 a certain condition causes D3 to become active, and due to this we get to the condition in the fourth clock cycle that T4 is active at this point and D3 is also active, because of which the sequence counter is cleared to 0. Once the sequence counter is cleared to 0, we start all over again from T0 again, similar to this point, and the entire process repeats for the following condition that when it is satisfied. Hence, the sequence counter responds to the positive transition in the clock. Initially, clear input of sequence counter is active, and the first positive transition clears sequence counter to 0, which in turn activates time signal T0 out of the decoder. Hence, we had T0 as active in the beginning for one clock cycle. The positive clock transition labeled T0 in the diagram will trigger only those registers whose control inputs are connected to T0. Hence, whenever T0 is active, only the registers that are connected to T0 are the ones that will be triggered and will be executed. Sequence counter is incremented with every positive clock transition, and clear input is active. Hence, it is set to 0 complete throughout the cycle. This produces a sequence from T0, T1, T2 and so on, as shown in the diagram. We saw T0 at 1 and then T1 was active, T2 was active and so on. If sequence counter is not cleared, then the timing signals would continue. They would not stop at T4. Instead, they would continue to T5, T6, all the way up to T15, since we have the decoder of 15 T outputs in the sequence counter, as we saw in the hardware program. And then after T15, it would have been set to 0. But since the condition was fulfilled where D4 and T3 were active, the sequence counter had been cleared, hence the timing signals stopped at T4. A memory read or write cycle will be initiated with the rising edge of a timing signal. If we assume that memory cycle time is less than clock cycle time, then a memory read or write cycle initiated by the timing signal will be completed by the time of the next clock cycle goes through the positive edge. The clock transition will then be used to load the memory word into register. The memory cycle time is usually longer than the processor clock cycle. So the first step is at T0 we have program counter that stores the initial instruction that needs to be executed. It is transferring it to AR, so the content of PC is transferred to AR at time T0. So T0 is acting during this entire clock cycle. During this time, the content of PC is placed onto the bus. Thus we have 010, as PC was denoted by 010, and then the load of AR is also set to 1. The actual transfer does not occur until the end of the clock cycle. Thus, when clock cycle goes through the positive cycle, that's when the transfer occurs. This same positive clock cycle increments the sequence counter from 0000 to 0001, hence a +1 increment in sequence counter. The next clock cycle has T1 active and T0 becomes inactive. We will be looking at this question to understand how the instruction is used to and how we identify an instruction as to what it is supposed to perform. So in part A we have the code in 4 different parts, and each of them has 4 bits. So we can tell from this that we could create a 4-bit hexadecimal number from this as follows. So 0001 tells us that it is a 0 addressing mode, that means it is a direct addressing mode, and 001 shows that it is a memory register reference because it is in the range from 000 till 110. Hence this is a memory register reference code, and the function that will be performed can be derived from the table, where we will find that for the following code the addition is the function. Then the remaining 12 bits are the address for the binary number, as we studied earlier. That means we will convert them into the hexadecimal values, 0000 being 0. This will give us 2, and this is a printing error. It's supposed to be 0100, and that would give you 4. And since we've converted it to hexadecimal, we have 16 as the base, 16 as the base. The output of this is 1, hence our overall code is 1024. 1 was the state at which we were performing addition, as we saw in the table. 024 is the value which is having addition applied to it. The operation that is being applied is adding the content of M024 to accumulator register. Hence this is the operation that is being performed. Similarly, we can take the second example where we have 1011 and we have these 12 bits that represent the binary 12 bits that represent the hexadecimal 124. This is 16 base, and for 1 means it is an indirect addressing mode, and we have 011, that means it is still a memory register reference. The function that will be performing is sta, which is store in A, okay, or store in AC, and hence from the 4 bits we can say 1011 gives us the hexadecimal value of B, and then 124, so B124 hexadecimal code for the binary we have converted, and the operation that is being performed is store AC in memory of 124. store indirectly 124. The reason we have double M over here is because it is indirect addressing, so the memory will be pointing towards another memory address which will be storing 124. For the third part we have 0111. This is register reference because it is 111, and since the addressing mode is 0, that means it is a register reference. And then we can convert this into the hexadecimal number of 0207 from here. As we saw in register reference, it is always 7, hence 7020 hexadecimal number, and at 020 we had the operation being performed increment AC, hence we will be incrementing the accumulator register. Thank you and see you in the next part.